would like to continue with this impulse function a little more, because it's very central and very important. Okay, so let me now switch over to the discrete time domain for some time, and then we will come back within the same class, because discrete time impulse functions are simple. So I would like to introduce a very important concept here, and it is very easy to introduce it with the help of discrete time impulse function. And once you understand that concept, we have to come back to the continuous time domain and discuss the same concept, okay, where it is slightly more involved, but with this background of concept that you learn from the discrete time domain, you will get it a slightly better way to understand. Okay, so the concept I want to introduce is this. So given an arbitrary signal, so we are in discrete time, so I will use this square bracket. So given an arbitrary signal x of n, okay, so let me just plot this, okay, x of n. So it is an arbitrary signal, you can take any signal, okay. So there is 0, there is 1, there is 2, there is 3, there is 4, there is 5. So let me take a simple case, -1, -2. So I can take any case. So this is 1, and then say this is 2. Let's say that this is the values. Everywhere else it is 0 here, and then let me make it more simple. Okay, so this is the values, and this is another value, this is another value, this is another value, this is another value, and then this is 0. Okay, everywhere else it is 0, I am assuming. Okay, it need not be 0. You can have arbitrary function. That's what I mean by arbitrary function. It can be any value. It need not be 1, 2 restricted to this and all. It could be any value. Okay, so this is the function that we have. I just plotted it. So plotting is a way of specifying the function. Another way I can specify the same function is this. Okay, I can give the values like this. So at -2 it is 0, so I will put 0, and then -1 I have 1, and then 0 I have 1, and then 1 I have 2, then 2 I have the function value 2 again, and 3 I have 1, 4 I have 1, and then 5 I have 0, 6 I have 0. Okay, so these are the only value that I have plotted. I am denoting it. So I can represent it like with the curly braces. These values I can specify. Now you may wonder, where is my which value correspond to which n value. So to avoid that confusion, what we do is we will put an arrow in the position corresponding to n equal to 0. Okay, you see n equal to 0 I have 1, the next value is 2, the previous value is 1. So that will avoid any confusion. So these are two ways in which I can specify the value of function. Okay, an arbitrary signal. Okay, it can be specified by drawing the graph or the plotting of the function, just like I have shown in the left side, or it can be specified by a curly bracket with entries 1 by 1. Okay, and or sometimes you can specify the value of the function by a closed form expression. Okay, just like I told you, sine omega n. Okay, and then when you put in the value of n, the sine omega n will have some value. So that is alternative. Okay, so these are arbitrary function. Yeah, it may have a closed form expression, it may not have a closed form expression, but the values are specified like this, and it is available to us. Now what I want you to do is, what we will do now is to express this x of n as the sum of shifted and amplitude scaled versions of impulse functions. Okay, so the task that we are undertaking, okay, the task, okay, and this is a central task, as you will see in this course. The task that is at hand is basically express, you need to get this very clearly, okay, express x of n okay, in terms of shifted and amplitude scaled, not time scaling, it is amplitude scaling. For example, multiplying x of t with some number, okay, so that is amplitude. So shifted and amplitude scaled versions of impulse functions. Okay, so this is the task, okay, this is our problem. So what we do, okay, is that we have this function, okay. Now I will draw a set of many curves, okay, again, and where this function is just like this, everywhere else it is this is our impulse function, okay, it is 0. So this is -1, this is -2, this is 0, this is 1, 2, 3, 4, etc. Okay, everywhere else it is 0 except here it is 1. Okay, I just took the value of this function, whatever is that, at n equal to 0 I put it there. Okay, so that is one function. Another function I am going to take, I can give name also, but let me just first of all do this much. So this is 1, and then it is 0, 0 here, 0 here, 0 here, 0 here, 0 here. Okay, so this is -1, sorry, this is -2, this is -1, 0, 1, 2, 3. Okay, all of these are 0. Only one point it has non-zero values, and that value corresponds to one of the samples. All right, next, so next is I am going to the right. Okay, so I have the value of the function at n equal to 1 as 2. So I will draw another function. Okay, and here I don't have value here, or sorry, I have value there. Okay, so this value I am having, that is 2. Here it is 0, here it is 0, here it is 0. So this is -2, -1, 0, 1, and then 2 it is 0, 3 it is 0, 4 it is 0, etc. So it has only one non-zero value, that is at 1, and there it is 2. So I am just separating this given arbitrary function into different parts, okay, different sub functions basically. That's what I am doing. Again, I continue this exercise. Okay, so 0, 0, 0, 0, and now 2, I have 2. Okay, so this is also 2, and then I have 3, 0, 4, 0, etc. Okay, then again continuing this exercise. Okay, 0 at -2, 0 at -1, 0 at 0, 0, sorry, this is 1, 0 at 1, 0 at 2, and then I have 1 at 3, 0 at 4, 5, etc. Okay, so this is 1. Okay, that's what I think I had. At 3 I had 1, and then so just to be sure I'm showing this level like this, and then one more place. Okay, so everything else is 0. Okay, one more place, that is 4. 4 I have 1, 5 I have 0, 3 I have 0, 2 I have 0, 1 I have sorry, this is 2, and this is 1 I have 0, 0 I have 0, -1 I have 0, -2 I have 0, etc. Okay, so these are different functions. Now let us give some names to these functions. Okay, so first function, this is basically delta of n, right? This is our delta of n. This is our impulse function in the discrete time, simple. And what name we can give for the second function? Here we have 1 at n equal to -1. So it is shifting the impulse function to the left by 1 unit. How do you write it? Delta of n plus 1. Agree?
Yes, sir.
Yeah. So what name, can you tell me now what name I can give for the next function? This function, it is 2 at n equal to 1. So what name you can give? Delta of
Delta n minus 1.
n minus 1, but that then amplitude is only 1. So I have to do amplitude scaling, right? So 2 into
2 times
delta of n minus 1. Very good. So you got it. So the next one, similarly, what name I can give for this one?
2 times
Delta
of
n minus 2 and multiply it with 2, right? Correct.
yes,
Very good. Next one, delta of n minus
n minus 3.
3. Okay, amplitude is 1. Okay, if it was different, I could have given that. Okay, so then
Yes, sir.
delta of n minus 4.
4.
Okay, so I got it, right? So now if I add all these functions, I will get back my actual function, right? You see that? So if I add delta of n with delta of n, okay, let me write it in the order. So first thing first, okay, in the order of n, let me write. So if I add delta of n plus 1 with delta of n plus 2 delta of n minus 1 plus 2 delta of n minus 2 plus delta of n minus 3 plus delta of n minus 4. Okay, that's it. So then I will get, if I add all of this, I will get my x of n. All of you agree with this? All of you agree with this? Do you agree with this? This is my x of n. So if I add all of these components, these are all individual functions. If I add all these functions, I will get back my x of n. Do you agree with this? S or S or no?
Yes, sir.
Very good. Okay. So now the same statement which I wrote here, I want to write now in a slightly different way. I will say, so I mean, I can have arbitrary amplitude for an arbitrary function. The amplitude could be arbitrary, but I can write these functions like x of say x of minus 1. X of minus 1 will pick me the amplitude at n equal to minus 1, right? So then I will multiply that with n plus 1 plus, okay, maybe I will take a new page and write this because it will be a long expression. So this keep in mind whatever I have written here, or maybe I will write it again. What I said is that if you add x of n plus 1, sorry, not x of n plus 1, delta of n plus 1, delta of n plus 1 with delta of n with 2 times delta of n minus 1 plus 2 times delta of n minus 2 plus delta of n minus 3 plus delta of n minus 4, I would get or maybe I will write the equality here, this side, this will be RHS, and then we will say that this is equal to this. So everybody agreed to this, and now I want to, so this is for a particular function. Now if I had a general function, then how will I write it? So for an arbitrary function x of n, okay, in this way I can write x of n is equal to, say, x, okay, I will put some dot 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 because I cannot write all the cases. I will put some dot dot dot, and then I will say x of minus 1 into delta of n plus 1, because I can have a different amplitude other than 1. Here it was 1, doesn't mean that every time it will be 1. Okay, for another function it may be 2 or 2.5 or 3, whatever. Okay, so that one will be given by x of minus 1 plus x of 0 into delta of n plus x of 1 into delta of n minus 1 plus x of 2 into delta of n minus 2 plus, okay, one more, let me write, x of 3 into delta of n minus, okay, 3 plus etc. Do you agree to this? Any function I can write like this. So when I say
Sir.
x of minus 1, this is just the value of the function x of n at minus 1. Yeah, questions?
Sir, that x of 2, sir, that was written sir, that x of 2 is it at amplitude, sir?
Yes, amplitude. The value of the function at n equal to 2, which was 2, right? Earlier it was, for the given function it was 2. This was 2. This was what? This was also 2. And this was 1. This was also 1. This was also 1, right? In
Yes,
the
sir.
earlier case it was those values, but now I am putting in a more general way. Okay, for an arbitrary function this need not be 1 always, it could be some other value. If it is some other value, then we need to take that value. But the point is that I can add these functions. So these are functions, okay, these are functions, and the other is just a coefficient, just a number. That is what you should notice. Okay, so
Yes,
we
sir.
are making a function, writing a function as the sum of many functions, and all the functions are what? They are impulse functions which are shifted by different unit, and each of them are multiplied by a factor which is which depends upon the actually the value taken by the original function. Okay, clear so
Yes,
far?
sir.
Okay, very good. So now I can write this infinite sum. There is an infinite sum, right? So I can write this infinite sum by using a sigma notation. So I will use k going from minus infinity to plus infinity. In general, the function can have infinite length, right? So here I have shown a function which has only finite length because everything else was 0. So you can say that it is a finite duration signal, but in general the function can be infinite duration. Okay, so now to incorporate all the possibilities, I am considering it as an infinite sum, and each term, what is it? So for example, this term is x of minus 1 into delta of n plus 1. So I can write like this, x of, so k take minus 1, when k take minus 1, it will be x of minus 1 multiplying with the delta of n minus k. You agree that if k is minus 1, it will be, if k is minus 1, it will give this term, k is minus 1, it will be x of minus 1, and this will be delta of n minus minus 1, that is n plus 1. Okay,
Yes, sir.
and k is 0, I will get this x of 0 into delta of n minus 0, which is delta of n. Okay, and similarly one more, when k is equal to 3. Okay, x of 3 into n minus 3. So you see that all the terms are coming out for different values of k. Okay, okay, so that is what we wanted to achieve. Therefore so what did we achieve? Therefore we got a very important result, that is any given function can be written as sum of infinite functions, infinite number of functions, where each functions are basically impulse functions shifted and amplitude scaled. So amplitude scaling is multiplication with x of k, and shifting is delta of n going to delta of n minus k. So this is what we wanted to show, and we have now shown it. Is that clear?
Yes, sir.
Yeah. So this is very easy to see for discrete time signal. Now we are going to go to the continuous time.
Sir,
Yeah.
sir, at the first, that graph and expression that you have written, sir.
Correct.
So can you go back there, sir?
Yes.
Yes. Yes, sir, getting arbitrary signal. Sir, in this condition, if we are given the right expression, then how will plot the graph according to that? It's like you have
Yeah. So
drawn the graph on the left side.
So the right hand side, you understand delta function, right?
Yes, sir.
Yeah. So what the right hand side is saying is you have to add, each term is basically a function. It is an impulse function at some location k. Okay. So for example, let us take a one particular function. So this is 0, 1, 2 and like that. Say somewhere you have k minus 1, k plus 1 and then like that. So this is n varying. Similarly minus 1, minus 2, etc. So if you take one term, what it says is that at k you have a value, and the value is basically the height. Okay, this height is basically x of k. So this function is basically x of k multiplying delta of n minus k.
Okay.
So
Yes,
this,
sir.
this is just one of those functions. So similarly there is a function for k minus 1, k minus, so for all values of k there are functions. So you have to add all these functions. So there are infinite number of functions, but if the function value is 0, so that will be like 0. There is nothing to add there.
Yes, sir. For it's a generalized expression for getting all these values.
Yes. So this is a generalized expression.
Yes,
So
sir.
you need to really understand what this expression means. This means a given arbitrary signal, we are expressing it in terms of the shifted versions of the impulse function. Each one of them are appropriately amplitude scaled by a factor. So I hope this is clear.
Yes, sir.
Okay. So now let's go to the continuous time domain, where it is slightly more so let me take a new page. Okay, so the purpose is the same, our task is the same. So let me first start with drawing a function. Right now this is continuous time. Okay, so continuous time. Continuous time domain. So this is t, and let me just take a very slowly varying function for our purpose, something like this. Okay, and this is our x of t. You can have any function. Okay, it's not that only this function, but just for the demonstration I take one function, just like I took earlier case also. Now we want to express this function in terms of the continuous time impulse functions, shifted and amplitude scaled continuous time impulse function. So that is our task. Okay, but now we will proceed it in the following manner. What we are going to do is, first of all, we are going to try to approximate this function by using pulse function. So let me define what is a pulse function. So the pulse function is defined as an amplitude. It has an amplitude 1. Okay, notice this is, let me call it as a p of t, and it has amplitude 1, but it has or p with a suffix delta, and width is delta. This is not impulse function, this is pulse function, because the height is 1 fixed, but width is delta, and it is located from 0 to delta. Okay, so first of all I am going to approximate the given function, and approximation will have some error, and then later we will try to minimize that error so that the approximation will become accurate. Okay, so the way we are going to do is, first of all we are going to divide this given function in steps. Okay, so that is like delta width. We are going to slice this function like this. Okay, similarly to the left also I will slice this function. So this is 0, so this is 0, and then slice number 1, 2, 3, 4, 5, 6, 7, etc. Okay, this goes on. I cannot show all, but this goes on. So this is a continuous time function, but I am just slicing it. So this is 1 delta, so this is 2 delta, 3 delta, 4 delta, 5 delta, 6 delta, 7 delta, and so on. And then what I do is, at the beginning of the slice, okay, so actually the amplitude is varying, right, but I look at the beginning of the slice, and whatever is the value I have here, I will try to take the same value throughout the slice width. Okay, so if I do that, I will get something like this, then like this, like this, like this, then like this, and then etc. So now are you getting what I am saying? So first thing I did is I sliced the given function, okay, with a width of the slice is delta, same as the width of my pulse function. So this is my pulse function. Okay, its height is unity 1, but its width is delta. Okay, its width is delta, and then what I am doing, I am using another property, and that is basically whatever is the value of the function at the beginning, that I am keeping it as the same throughout the entire pulse. So my approximate function, now if I plot it, okay, my approximate function will be looking like this. Okay, and then a step, fix it, then another step, fix it, then another small step maybe, then fix it, and then like this, and then I remain, then I come back, slightly less, slightly less. Are you able to see what I am trying to say?
Yes, sir.
If the function is decreasing, my step will be like this. If the function is increasing, it will have this. So whatever was the beginning, so what is the value of this slice? It is basically the value of the function at the beginning of that slice. So that is maintained. The function will be changing during that step, but I will maintain the value, whatever I sense the value at the beginning, that will be. Okay, so I can now maybe draw this function here like this. So there is some error actually in the process. There is some error. Okay, but right now we are ignoring that error and trying to approximate the given function x of t. So this I will call this function as x with a suffix. So this is not square bracket, this is continuous time, so it will be x delta of t. Now I can approximate the x delta of t. Okay, so that was unintentional. Okay, so now I want to construct x delta of t using the pulse function. So how can I do that? So x delta of t is basically what? So this is the pulse function. If I take the pulse at t equal to 0, so this is the pulse at t equal to 0, so that is multiplied by the value of the function at 0. I am multiplying it with the p delta of t. Then okay, so I have some dot also here. So let me just rub this. There are lots of terms here, and then I am picking up one term here, which is the central term corresponding to the pulse at t equal to 0. What is the height I should have? Pulse function has a unit height, but I need to change that height to whatever is the height of the value of the function. So that is given by x of 0. X of 0, I am multiplying it with the p delta of t. Okay, the next pulse. So I am just taking, so far what did I do? I only did this function. This is what I did. Okay, this is the function. I have splitted this into one particular one. Then I am, the second slice I am showing it with a different color like this. Okay, and the third one I am showing with another color. Okay, like this. So I am taking different functions and adding them. Okay, so the first slice is this, and then let me use the next color. This is x of delta. Okay, x of delta, because that is the beginning of the pulse. Okay, multiplying with the x of delta is multiplying with the p delta of t minus delta. So that is the pulse which I have added, the green pulse. Then I am adding the orange one. Okay, orange one will be what? It will be x of 2 delta. Okay, so this is the location delta, and then this location is basically 2 delta. Okay, and this is basically 0. X of 2 delta, and then multiplying with the pulse located, the shifted version of the pulse function, p minus 2 delta. Okay, are you with me?
Sir.
Yes.
Sir.
Yes.
So p t minus delta, is it basically a
shifted version of unit pulse function? This is a pulse function. Okay, let me just plot it here. Okay, so if you have a confusion, let us clear that. So
okay, sir.
I have
shifting by t times.
Yes.
Delta times.
2 delta times.
Yes. Yes.
Okay, so this is my p delta of t minus 2 delta. Why I say 2 delta? Because this point is 2 delta. This is my delta and this is 0. So this function underwent a transformation, t going to t minus 2 delta. That's all. And then I am amplitude scaling in order to adjust its height. This height is 1. So I need to adjust the height with respect to the height of the actual function at 2 delta, t equal to 2 delta. Clear?
Yes, sir.
Yeah. So now I can do this exercise to the left also. So let me take so another color. So here is so if I extend this, it will be like this. So this will be the slice here. So that slice, the purple slice, is basically x of minus delta. So this point is minus delta, and that whatever is the height that remains throughout the slice duration, multiplying p of delta t plus delta, right?
Yes, sir.
Yeah. So this way you can keep on going. So what are we doing? We are trying to write x delta of t, not x of t. We are trying x delta of t, which is the approximated function. Okay. So this I can now use summation, right? I can use summation, and I can write like this: sigma. So can you tell me what should I write? K going from minus infinity to plus infinity. How will I put it? X of k delta into p delta of t minus k delta, right?
K delta. Yes, sir.
Correct. So this is the simplified version of the infinite series. Okay, we have an infinite series, sum of infinite terms. Each of them is basically a pulse function shifted by some unit and scaled by some factor, and we are adding all of them together. And what are we getting? We are getting basically this right hand side, x suffix delta of t, which is an approximate version of x of t. Actually we have x of t, but first thing we did is we approximated it to get x delta of t, and that is what we have. Now what can we say between x delta of t and x of t? What is the relationship between them? If we make delta tending to 0, then we will get x of t, right? X delta of t, in x delta of t, if you take a limit where delta goes to 0, we will get the actual function x of t. Do you agree to that? That means if the width of this slice is reduced to 0, we will get the actual function we started with, not an approximation. The approximation become accurate. Do you agree to that?
Yes, sir.
So that is what we will do next. Okay, so we will specify now limit delta tends to 0, x delta of t is equal to x of t. That is, limit delta tends to 0. Okay, what is inside? Sigma k going from minus infinity to plus infinity x of k delta into p delta t minus k delta. Okay, so this should give me x of t. Okay, so we have just substituted this, right? So what I am saying is, so that is x of t can be written as this. Okay, so this is equal to, now when you make delta t tending to 0, what will happen to this expression? That we need to see. There are two terms here. One is x of k delta, the other is p delta of t minus k delta. Two terms are there. So what I will do is that, in order to see that clearly, I will do some algebraic manipulation, and the manipulation is this. Okay, minus infinity to plus infinity. I did not do anything here. What I am doing is, I am going to multiply this with delta. Okay, multiply this with delta, and then I can divide with the delta, and divide with delta. Okay, this is just an algebraic manipulation. One term I multiplied with delta, another term I divide with delta. That's all I did. Okay, now I am taking the limit of each of this term. So this is just an algebraic step. What did I do? Earlier there was no delta here. So x of k delta I multiply with delta. P delta of t minus k delta I divided with delta. I divided with delta. I did not change the value, right? I can cancel this delta and get back to the previous, right? Agree? Are you with me so far?
Yes, sir.
Yeah. Now if you look at the second term, this is a familiar term to you. What is it? Can you tell me what is this? In the limit, this is familiar to you. Limit delta tends to 0, p delta t minus k delta divided by delta. What is this? Let me draw this. Let me draw this. So p delta is, first let me draw p delta. So this is 1 width delta. Delta is a width, height is 1. So this is my p delta of t. Now in the limit, I am changing the limit or width delta going to 0, and then I am multiplying p delta with delta. Understand? Or in other words, if I multiply this with 1 by delta, what will happen? So this is p delta. Now let me also draw another function here. Okay, so this is my time. Okay, I'm multiplying with 1 by delta. Delta is very small, so I have, this is delta and this is 1 by delta. And what is this function? 1 by delta I multiplied with p delta. Now I am taking the limit. I am taking the limit delta tends to 0. What will happen? 1 by delta will become smaller and smaller. Width will reduce. I will have something like this, right? From this I will get thinner and thinner, but height is going up and up. So what is it? This is with a smaller value of delta in the limit. So as I reduce this delta value, what is going to happen is that this is going to become, so this limit delta tends to 0, 1 by delta, p delta of t is going to be what? What is this? If I reduce this, yes, unit impulse, very good, right? So this is basically the definition that we have seen earlier. This is basically delta of t. So we identified one of the term as delta of t. Okay, so that is only in the limit delta goes to 0. Now when delta goes to 0, delta can be identified as what? Similarly, so that you keep in mind. So we are going to write it again. So that is x of t is equal to limit delta tends to 0. We had two terms, x of delta, what was it? X of delta into k delta, right? It was k delta, x of k delta into delta. So that was the first term. Then we had other term which was p delta of t minus k delta divided by delta. Okay, so that's what. Let me just verify whether what I wrote is correct. Going back, yeah, x of k delta into delta and then p of, so I have some more detail here. So this is basically, this is not correct. So this is basically delta of t. And what about this t minus k delta? T minus k delta. So what is this? I have to say that again. Okay. So again, let me come back to again. So delta is going to 0. So I can say that it is d tau, infinitesimal. Okay, delta going to 0. So that means I will call it as just like differential element, d tau. Okay, I will just call it like that. And then k into delta in that limit. So this is the limit we are seeing, delta tending to 0. In the limit delta tends to 0, delta will become d delta, or maybe I should write like this, equal to. So in the limit delta goes to 0, so delta is equal to d tau. K delta become tau. Okay, there is a summation also here, right? I left the summation. Okay, summation I can put outside also. Summation I can put outside also. K go from minus infinity to plus infinity. Okay, I have taken the summation to be outside. Okay, so let me continue. So delta become d tau. That's a definition. Okay, these are definition. And k delta become tau. Then what else? X of k delta will become x of tau. Okay, then what else? P delta t minus k delta divided by delta becomes, all of these are happening in the limit delta goes to 0. This is basically delta of t minus tau. Okay, this is k delta become tau. So p of t by delta, we saw that it become delta of t, but p of t minus k delta will become delta of t minus tau. Are you clear with all of this? If there is any doubt, you please ask. We can repeat it, we can go over it again.
Sir?
Yeah.
So is it that delta a small quantity, sir?
Yeah, so delta is tending to 0. It is not exactly 0. Okay, it is tending to 0. So we are calling it as d tau differential. No, so that's the definition of differential. Also, if you look at we start with slicing a function like integrations, not differential, integration. When you say, when you define calculus, in calculus, when you define integration, what we do is basically we start with some function, we say something like this, and then we will do this slicing, right? This is t, and then we say that initially we say that this is delta t, and then we say limit delta t, limit delta t goes to 0, delta t will become dt. And then we are basically adding all the areas of each slice, and that will give you the integral. That is how integral f of t dt comes. It is basically in the limit delta t goes to 0, f of k delta t into delta t. Probably you might have studied this, no, in calculus.
Yes, sir.
Yeah. So there is a sigma also. Okay, sigma over k from one point to another. Then so even if you don't know that also, it's okay. It's not necessary, but it is similar concept. If you're already familiar with this concept, then it become more easy. That's all. Otherwise also I am explaining it here. So delta tends to 0. So if delta is what? Width of the slice. So it tending to 0, we need to denote it with some other notation, which is basically d tau. I am calling it as d tau. So, or maybe you can say that instead of delta, I could have called it delta tau. And in the limit delta goes to 0, delta tau goes to 0, I will call it as d tau. Okay, delta tau becomes d tau. This is a limit where delta, the width of the slice becoming almost 0. So that is d tau. Now k into delta, k into that width of the slice, k is a number that runs from minus infinity to plus infinity, right? So that will become a finite thing, because k can be infinity also, delta is tending to 0, so it's like a combination of both product. So that will become a finite number, tau. Okay, x of k delta become x of tau. So p delta of t minus k delta by delta,
yes, sir,
becomes delta of t minus tau. Okay, so we are now putting it all together in this expression, and then we will remove the okay, so we can keep the summation for some more time. So this is basically summation. Now it is summation over tau. Okay, the summation will become actually integration. So this is an integration with respect to tau. The first term is what? X of tau, and then there is a d tau, and then so that is the first term, and the second term is delta of t minus tau. And when k goes to minus infinity, this will become minus infinity. When k goes to plus infinity, it goes to plus infinity. Okay, so d tau, it's not 0, it's very, very small. That's what it's meaning. Okay, multiplying it with infinity, you will still get infinity. Infinity will overpower actually. Okay, so if you multiply with minus infinity, it will become minus infinity. If you multiply with plus infinity, it will become plus infinity. So now I am going to rearrange this and write it as integral tau going from minus infinity to plus infinity, x of tau into delta of t minus tau d tau. What is this? This is my x of t. This is the analogous expression. So since this was slightly more complicated than the discrete time, okay, that is why I introduced the discrete time first, and then the concept is the same, but here we had to approximate the function. We did it in two steps. We first approximated it with a step function, like this kind of staircase kind of approximation, and then in the limit this delta goes to 0, we claim that it will become approximation become exact. Okay, so the written summation here, so this is the approximate function, and then we took delta tending to 0, and then we did some algebraic manipulation in order to bring our impulse function into the scene. It's a pulse function. If you divide it by delta, it is an impulse function in the limit delta goes to 0. Okay, and then when you took the limit delta goes to 0, delta is basically width of the slice, in the limit we got this integration. Okay, summation is basically integration. Okay, we are basically multiplying we are basically adding up the area of each slice basically. So that is what is integration by definition. Okay, so this is a summation notation and this is integration notation. When the summation become so small slices you are adding up, so that can be treated as integration. Integration means that basically.
So then it is basically describing a complete curve.
Yeah. So if you look what does this mean? If you look at, you are seeing that t is the variable on which the function is defined, and on the right hand side the t is where? T is with respect to the impulse function. Okay, so this is basically a coefficient. X of tau is basically, this is a coefficient, whereas the function is here, this is a function. So the function is shifted, impulse function is shifted by tau unit, that is delta of t minus tau. It's a shifted function, and then it is multiplied with a coefficient x of tau.
Yes, sir.
Yeah, so it is the same idea that we saw above. If you look here, the same thing you can see here. In discrete time domain, you had an impulse function. Okay, so this is our function. So this is a function. We are expressing one function in terms of another function, and each function is a shifted version of impulse function and multiplied with some amplitude. Okay, so here this is amplitude. Okay, so it is the same idea, but one is in discrete time and the other is in continuous time domain. But continuous time domain, you need to do some little bit more algebra and then little bit so taking of limits, etc. But otherwise the idea is the same. Is that clear?
Yes, sir.